is my great pleasure to introduce Dr. Nithin Nagaraj. And I know Nithin Nagaraj for a very long time. And he was a good friend of one of my PhD students, Nirmal Jagu.
Yeah.
So, and basically, he has a typical engineering background. He did his bachelor's degree from NIT Surathkal, master's degree in electrical engineering from Rensselaer. After that, he stops being typical. Okay. So he got his PhD from NIAS, which is an interdisciplinary institute in Bangalore. And he has worked in a variety of places like Global Research, IISER-Pune and Amrita University. And now he's working as an associate professor in NIAS on the IISc campus. So his research areas actually are quite eclectic. So he works on chaos and information theory, complexity theory, and he also has worked in neural networks. Then he's a senior member of IEEE, and he actually is the inventor of eight US patent applications, of which 2 have been granted, and an Indian patent application also. So from the engineering point of view, he has just the kind of background which you people would have aspired to. I mean, engineering students would aspire to. And given his background, his topic is exactly in line with his background and also in line with the topic of the workshop. So remember that while a lot of the talks in the workshop have been concentrated on reservoir computing, it also actually involves in what ways neural networks and dynamical systems contribute to machine learning, okay, and AI. So his topic is, can chaos and noise help machine learning? And okay, I won't stand between you and the speaker. Please.
Thank you very much, Professor Nilima, for a very generous introduction, and I'm very happy for the invitation, firstly, for giving this opportunity. And let me share my screen. Okay, is that visible to all?
Yes, sir.
Okay. So yeah, so let me begin. Yeah, I think I'll start with acknowledgements. I thought, so basically this is joint work with, 2 of my PhD students, mainly PhD student Hari Krishnan, who's now a faculty at BITS Goa. So much of the work that you're going to see today is going to be his work actually, and a bit with Aditi as well. And Aditi is going to talk later today, so you'll listen to her as well, and a whole bunch of other people whom I'm very grateful to. So the plan of my talk is as follows. I want to sort of give a brief motivation for brain-inspired machine learning. And then I'll talk about the hero of the talk, the main character of the talk today, which is neurochaos learning. And expressed in form of an equation, the idea is chaos plus noise is equal to learning. I mean, is it even possible that such a thing is possible? And then we'll talk about some concrete results and some discussion. And then I will try and touch upon reservoir computing, though I would say that a disclaimer that there is hardly anything on reservoir computing in my talk today, but later I think Aditi is going to talk a little bit as well. So that's the promise for today. Okay, so let's begin. I think it all started in summer 1956, right? This Dartmouth conference organized by John McCarthy in the US, where a bunch of people, they came together to write a proposal and they coined the term artificial intelligence. And what you see here is a typical Venn diagram, right? Machine learning and deep learning. And of course, we know the tremendous advancements which has happened since then, since 1956. And the claim is always that ANNs and many of these algorithms are inspired from the brain. I mean, that's usually the claim. And we will see how true the claim is, okay? Now, what is very interesting is that the idea of a neuron, the artificial neuron itself, was actually before this, 1956. It was 1943. This amazing paper, a collaboration between a neuroscientist, Warren McCall, and a logician, Walter Pitts. They wrote this paper where they sort of brought the artificial neuron to life. And we know that rest is history, right? That you have this tremendous growth in deep neural networks, which kicked off, I think, 2011, 2012 onwards, thanks to GPUs and all kinds of fast algorithms and hardware and, all kinds of stuff. And we know that deep neural networks today are a force to reckon with, right? I mean, they're hugely successful in all kinds of tasks, speech recognition, image recognition. AlphaFold, you might have seen the news very recently, right? That they're able to predict the 3D structure, the protein structure using an amino acid sequence. And it does far better than any of the other techniques, right? So that's quite a leap in, in kind of genomic science, you can say. And deep learning is the engine behind AlphaFold. And there are many, many more. I mean, there probably this one, you can't even have a single talk on deep neural networks itself. So I'm going to just sort of summarize it here. Now, but I'm going to say that my view is to throw it all away and start again. Of course, it's not my view. It's not my view. This famous quote was by this gentleman here. I think many of you probably recognize him. He is the 2018 Turing Award winner, Geoffrey Hinton, who is also the godfather of deep learning. So thanks to his paper in 1986, the backpropagation paper, that we have deep learning today, right? And backpropagation algorithm is the algorithm that helps us to update the weights or train the weights from data, right? And that's how the whole deep learning actually works. So it's very much the heart of deep learning. And even today we use backpropagation. So Hinton was interviewed a few years back. I hear some noise in the background. Yeah. So Hinton was interviewed a few years back, and he said that, look, we need some radical new ideas. We need some radical new ideas, and his point was that we should probably throw it all away and start again. Now, I mean, if we take it seriously, if we take his word seriously, and what would that look like? So I thought, let's start all over again. And then we can go back 13.8 billion years, right? We can rewind the clock. And the Big Bang, whether it happened or not, we don't know. But let's say that we go 13.8 billion years ago, and the universe expands, and then closer to today is, let's say, 3.8 billion years ago is when life started on Earth. And what is impressive is the kind of complexity of the cerebral cortex. So once you enter of course, we were swimming and crawling, and then we slowly now stand on 2 legs and all that. But in this journey of evolution, once you enter the mammalian species, you notice the enormous increase in the complexity of the neural complexity, right? In the cerebral cortex, for example. So these are just some numbers here. So notice that an elephant would have 5.6 billion neurons. A gorilla would have 9.1 billion neurons. A chimpanzee has 6 billion neurons. A human is roughly an elephant and a gorilla put together. I mean, or more, slightly more than that. 16.3 billion neurons. So that's the kind of complexity that we're talking about. And then you could also do the following, right? You could compare, you could ask the question, what should we compare the brain to? And it turns out that you have to compare to the galaxy, because the number of stars in the Milky Way galaxy is roughly somewhere between 200 to 400 billion stars. And our brain has something like 86 billion neurons, with 100 trillion synapses. So this is a slide which should cheer people up, right? If you're feeling down, I tell people that, look, I mean, it can be students or anyone for that matter, that, look, you're carrying literally a galaxy of stars in your skull, which are all twinkling and firing, and all these neurons are firing, and it's enormous. I mean, it's incredible to even think about what we are capable of, right? And interestingly, the structure of the universe and the laws that govern it is not that dissimilar from the way the human brain itself has evolved. This whole thing about network cosmology, which tries to study how networks evolve, has shown this equivalence. Now, if you look at the brain itself, right, it is the ultimate machine. I mean, there's no question about it. 3.8 billion years of evolution has resulted in sort of a perfect, I mean, may not be perfect, but by any human standards, by any engineering standards, it's really the ultimate machine. High complexity, the scale of it itself is very large. There is huge amounts of neural noise and interference. So there is this recent paper which talks about measuring the signal to noise ratio at a subthalamic neuron, and it's somewhere around minus 29 decibels. I mean, just imagine, right? A human engineering system would not even function at that low SNRs. And there's more. There is multiplexing and demultiplexing of neural signals. There is extremely low power computation. So this is again a sort of a back of the envelope calculation, which shows that a simple resting state thinking activity would sort of amount to 12.6 watts. I mean, that's really literally nothing, right? When you look at modern computers. I mean, this is hardly anything. And more importantly, we don't know how it works. And it's not me saying this. The famous neuroscientist V.S. Ramachandran makes this point that the brain science is still at a very early stage of understanding. They're called the Faraday stage. So we really don't. We have heuristics and we do understand a little bit, but largely the brain is still a mystery. That's the point I wanted to make. And if you compare the human brain to deep learning or AI for that matter, the comparison is quite stark. It's really stark. For one thing, a deep neural network consists of dumb neurons, right? Just linear superposition of neurons with some nonlinear activation. Whereas literally there is this chaos in the brain, and we'll talk about chaos very soon. And the brain has they talk about thousands of different types of neurons, and they broadly classify it into 5 subtypes. There are 1,000 of them, but they based on function and structure, they either say there are 3 types or 5 types, but there are a huge number of varieties of neurons. But we don't really see that in any of the deep learning architectures. And what is interesting about deep learning would be that, for example, if you look at the GPT-3, right, that's the latest offering by OpenAI. It's a deep neural network, natural language processing model, which produces very human-like text. In fact, it's sort of evaluated to produce very much like a human producing prose. But if you look at the statistics, if you look at the numbers on how the GPT-3 works, right, and what does it involve, I'll just read out some numbers, and I would say hold on to your chairs. It's quite shocking. GPT-3, the deep neural network model, has 175 billion parameters to be trained, 800 GB of storage. It requires 355 years of computing time, and believe it or not, the energy consumption is 200 megawatt hours. And what about the cost? The cost of training a single run of the deep neural network model is $4.6 million. That's the estimate that people have come up with. And more importantly, the huge carbon footprint. So there was a nice study by University of Amherst a couple of years back, 2019. There's a nice paper by this group from University of Amherst. What they showed was this GPT-3, I think, or maybe the GPT-2, I think, I'm not sure. These kind of models, if you look at how much of carbon footprint does it leave in the environment, right? They compared it to 5 cars. So you take 5 cars and run it for a lifetime. So you run these cars for a lifetime, 5 cars, and you count the number of, you accumulate that carbon footprint emissions of those 5 cars for the entire lifetime of that car. The training of this neural network would be equal to that. It's unthinkable, right? It's huge carbon footprint. The brain is not even a fraction of this these kind of numbers. And of course, we know the rest, right? You need large amounts of training for the deep learning, very poor generalization capabilities. We usually have a lot of overfitting. Then, of course, the brain is massively parallel. Of course, we do have parallel computation in deep learning. It's not that we don't have, but the amount of parallel computation in the brain is of an order of magnitude, several orders of magnitude higher than human engineered systems. And I already talked about SNRs and all that, right? So, and last but not the least, the whole thing about causality, right? So, and Ajit is going to talk about this more, that at the end of the day, one can argue that all the AI methods are just doing some kind of correlations. But what we really need is counterfactual reasoning and causal reasoning, which the human brain or the mind or whatever you can call it, the human system, or even for that matter, animal systems could also compute. So clearly the comparison with the brain is a bit too childish, I would say. We're very far away from the brain by all these parameters. Okay, now the question is, we would want to question the core of deep learning, which is the neuron. And the neuron is not very different from the 1943 neuron. It's slightly different from that, but it's still a artificial dumb neuron, which does linear superposition and followed by an activation function. But what we know in the brain and in the nervous system is that there is chaos in the brain. And this is well documented, a lot of empirical evidence. And that's the point of motivation for us, that chaos is very much at the core of learning in the brain, and we should harness the power of chaos. Now, what is chaos? Again, I know that I wanted to keep my talk a bit self-contained, so I thought I'll have a brief digression on chaos. I will not, it's obviously not going to be a very technical exposition of chaos, but I thought I should just impress upon you what the notion of chaos is, especially for the young audience who are not in this area. They should have some notion of chaos. So chaos, roughly speaking, is the unlikely marriage between determinism and unpredictability. That's the funny thing, right? It's deterministic equations, but producing unpredictable outcomes, unpredictable behavior from in terms of predictions and modeling the system. And it comes about because of nonlinearity, mainly nonlinearity, and some kind of iterative processes, right? Dynamical iterative processes. It could be in the form of a map or a flow. And it looks and feels like randomness, but it's just the opposite, right? It looks like randomness, but it's full of order and structure. You have periodic trajectories, you have periodic orbits, quasi-periodic orbits, you have non-periodic orbits, and more importantly, you have the butterfly effect. I think speakers yesterday talked about it, right? What the butterfly effect is, but I think the popular image is the butterfly effect, which is the flapping of the wings of a butterfly in Kanyakumari can start off a snowstorm in Kashmir. Well, this is actually not quite true. It's not really a statement of causation. It's more a statement of prediction. Actually, it's not the case that the butterfly will cause the snowstorm, but the fact that small errors in computation would cascade very quickly due to the nonlinearity, and what you end up predicting is two different scenarios, which are very different from each other. And technically, we can talk about chaos has all these dense periodic orbits, topological transitivity, and Lyapunov experiments being positive. Now, but I think I thought I should have this slide, especially for all the movie buffs actually in the audience. One of the best description of chaos is in Michael Crichton's novel Jurassic Park, which was also made into a very successful Hollywood movie. But for all the Tamil movie fans, there's a movie 12B. I've not watched the movie myself, but it's actually very similar to the Sliding Doors movie, which I've watched actually, wherein the hero of the movie is going for a job interview, and he misses the bus. The bus is 12B, and then the movie sort of bifurcates into two scenarios. What if he had taken the movie and taken the bus, and what happens if he does not take the bus? This is the sensitive dependence on initial conditions, right? The two trajectories are very, very different. Sliding Doors is similar. So this is the popularization of chaos in the common public. Now, let me give you a more concrete example so that it will help you for the rest of the talk. So take this simple algorithm, extremely simple algorithm. You start with a number between 0 to 1, a real number, and you multiply by 10 and you output the integer part of that number. And then you replace the number with 10x minus that integer part. I'll give you an example just to show you. So let's say you start with 1 by 7. So first step is you multiply by 10 and output the integer part. That will be 1, what you see in the red color here. And then you replace the input 1 by 7 with 10 by 7 minus 1, which is 3 by 7. And now you do the same thing. You multiply by 10, you get 30 by 7, take the integer part, which is 4, output it, and then again replace the x with 30 by 7 minus 4, 2 by 7. You keep doing this, you end up getting 1 by 7 after 6 iterations, right? You see the bottom part of the slide here. So 1 by 7 goes to 3 by 7, goes to 2 by 7, to 6 by 7, 4 by 7, 5 by 7, and then you come back to 1 by 7. So it's a period 6 trajectory. It's a period 6 trajectory. And what you see in the red color there, 1, 4, 2, 8, 5, 7, that's the symbolic, it's called the symbolic sequence. That's the output. And this algorithm is nothing but long division. I mean, we all know this, right? We all studied in grade school. We all know this. But our math teacher never told us that this is actually an example of a chaotic map. This simple looking algorithm, which extracts decimal numbers, decimal representation, expansion of a real number, is actually a chaotic map. What I mean by that is that you could plot the first return map, 10x minus integer part of 10x. It looks like this. You can see this 10, it's a piecewise linear map. And it has all the properties of chaos, which means what? Which means that you have periodic trajectories or periodic orbits, like the rational numbers, right? You start with the rational number, like 1 by 7. You have periodic orbit, like 1 by 7 has period 6. But you also have non-periodic trajectories. For example, the decimal expansion of the number pi, right? So, I mean, that will not be periodic, or irrational numbers, root 2 or 1 by root 2 or whatever, And there are uncountably infinity of them. And very importantly, you have this sensitive dependence on initial conditions. So you start with any number, you could have a periodic trajectory. You perturb it slightly, you might end up having a non-periodic trajectory. And this is actually the reason why you could have rational approximations to the number pi to any desired accuracy that you want, because of this sensitive dependence, right? That you can have very different behaviors qualitatively, two numbers which are very close by. One can be periodic, one can be non-periodic. So that's that point, right? So it is all the properties of chaos. And you could also do it with binary expansion. So you don't have to do 10x minus integer part of 10x. You could just do 2x minus integer part of 2x, and that would be the map I show you here. It's a very simple piecewise linear map, which is with a positive Lyapunov exponent. So the Lyapunov exponent is basically a measure of the rate of divergence of nearby orbits. That's one way, nearby trajectories. That's one way to think of it. how quickly do errors cascade? How do you measure that? It's a measure of that rate of that divergence, basically. But you could also do other maps. You could have the tent map, very, very popular map. You have the logistic map, which is very, very important in biology. It's a sort of a toy model for population dynamics, right? How species evolve, like the example of Jurassic Park, right? So you have all these unstable, or you can have periodic oscillations of the population, the number of species in the population, basically, right? The logistic map, the tent map is here, and then you could have skewed version of the tent map, right? You could have this skew binary map and a skew tent map. Basically, what I'm saying is that the tent map is symmetric about 0.5, but you don't have to have that symmetry. Now, these maps are important for this talk because they all fall into this general family of maps called generalized Lorentz series, or GLS. I'm going to call it as GLS from now on. So GLS is a very interesting set of maps, the piecewise linear maps, what I just showed you now, the tent map, the binary map, the skew binary map, the skew tent map, the decimal map. All those maps are all examples of GLS, and they're actually studied for number theoretic properties, ergodic theory of numbers, basically. Like you look at all these mixing properties and amazing number theoretic properties, expansions of these kind of maps. It goes all the way back to Lorentz's work and Cantor's work, actually. Just to give you the most general version of a GLS map, you have this map here. There are what's called a generating Markov partition. Basically, you have these n, you can see n intervals on the x-axis, right? 0 to 1, a1 to an, and in each of those intervals, you have this a piecewise linear mapping all the way from 0 to 1. That's important. It's all the way from 0 to 1, but you could have a positive slope or a negative slope, right? So the slope is 1 by p1, 1 by p2, 1 by p3, but you could either have positive or negative slopes. So basically, you will have n factorial different maps where you can permute them, and you can have, you can have various maps which are all equivalent for this. They're all sort of conjugate, not necessarily topological conjugate. They're semi-conjugate, or they're equivalent maps, basically, which have all the same Lyapunov exponents, actually. So this is the most generic version of the GLS maps, and these maps are very, very special, partly because of this amazing equality. The Lyapunov exponent of these maps is exactly equal to Shannon entropy of the symbolic sequence. Remember, what is the symbolic sequence? You start with an initial value on the map. So for example, here, I could start with a number between 0 to 1, and I keep iterating the map, right? I keep iterating the map. Recall the example of 1 by 7, right? 1, 4, 2, 8, 5, 7. That was a symbolic sequence. So here, for example, you just record where the trajectory falls in this A1 to AN and give a symbol for that. A1 can be 0, A2 can be 1, A3 can be 2, and so on and so forth. You record the symbols, basically. You just record which interval I'm falling in each iteration. That's called the symbolic sequence. What you can actually show is that the Lyapunov exponent of the map is equal to Shannon entropy of the symbolic sequence. The only change you have to do is that the base of the logarithm. So typically in Lyapunov exponent, we use the natural, it's a natural logarithm, right? The base is E, whereas in Shannon entropy, we use the base 2 because we measure in bits. But for that constant of proportionality, they're exactly equal, which is actually very nice. You can interpret the Lyapunov exponent as in a very information theoretic manner. You can think of Lyapunov exponent as telling you that it's the amount of information, the number of bits of information of the initial condition or the initial value, which is revealed at every iteration of the map. So as you keep iterating the map, you're getting more and more information of the initial value. And how much are you getting it? That can be quantified by Shannon entropy or the Lyapunov exponent. So it's a very nice equation. And this allows for a whole bunch of amazing applications in engineering. So we have shown that you can get optimal lossless data compression because of this this bridge between this dynamical properties and information theoretic properties. We can use it for data compression, and you can actually achieve the Shannon bound for lossless data compression of IID sources. In fact, it's a generalization of an algorithm called arithmetic coding, which is used in JPEG 2000. So it's very heartening to know that the algorithm used in JPEG 2000 is actually a chaotic map, basically, right? It's a kind of GLS map. And there are a whole bunch of other examples for error correction, encryption, multiplexing. There's a whole bunch of work by Sudeshna Sinha and her group, pioneering work by them in terms of computing, using these kind of maps. Phenomenal work being done. And of course, you can also use it for communications and pseudo random number generators and all that. So all these, partly it's because of this handshake between dynamical system properties and information theoretic properties. You can actually prove many theorems, and you can give guarantees for many of these kind of applications. Okay. So now let me go to the hero of the talk, right? The neuro-chaos learning. Okay. So I've just sort of given a crash course on chaos, the most important aspects of chaos. But how do we use chaos in neural networks? So this is like a work that mainly my student Hari Krishnan, PhD student, did, and the past few years we've been working on these ideas. So we thought that we're going to incorporate chaos in the ANNs. And the word neurochaos is actually inspired by this paper, the paper in 2003 by Korn and others, where they showed that they coined the term neurochaos in that paper. The reason being that chaos is actually found empirically at all levels of hierarchy in the brain. You have chaos at the level of single neurons, coupled neurons, network of neurons, and so on and so forth. So chaos is all pervasive in the brain and nervous system, and they coined the term neurochaos. So we thought, okay, we're going to use that term, and then we're going to see how to do it now. So what's the architecture? The architecture is extremely simple. So this is actually the most important slide maybe for this talk. So the way it works is the following, right? You see C1, C2, Cn. That's the input layer of the neural network, the neural cluster learning architecture. And these C1, C2, Cn are basically the GLS neurons, what I just introduced, right? The skew tent map, the skew binary map, you could also have decimal map or whatever. I mean, you could have all those piecewise linear maps. That would be the GLS neuron, and that's the neuron, the C1 to Cn, each one of them. And X1 to Xn is the input data. So for example, let's say you want to do classification of, say, dogs and cats, right? You have image of dogs and image of cats. So you take the pixel values would be the X1 to Xn, right? You're feeding the input to the input layer of the NL architecture. And the way the algorithm works is the following, right? You have the first block is feature transformation, where C1 to Cn, which are all these chaotic maps, the chaotic neurons, they fire from an initial value queue. They all have the same initial value queue, and they keep firing until and unless they come very, very close to the stimulus. What I mean by the stimulus here is the input data, X1, X2, Xn. They're all real numbers. We normalize it to lie between 0 to 1. And for example, the pixel value, right? The pixel value of the image of the dog, right? It's a number between 0 to 255, let's say. It's a grayscale image. We normalize it so that it's between 0 to 1. And that real number is input to C1. And the chaotic map will keep firing until and unless it comes very close to the neighborhood of this particular number. And once it comes very close, it will stop firing. The neuron stops firing. What this means is that each of these neurons will fire for different lengths of time. So in this example, for example, X1 is fired for longer duration, X2 is fired for a lesser duration, and so on and so forth. Xn is intermediate. And once it stops firing, we then do what is called as neurochaos feature extraction. We go to these neural trajectory, the chaotic trajectories, and we extract features from that. And after we extract features, we then feed it to a classifier. And there are many options we can have. We could have a very simple classifier, which uses some very simple notions of similarity using a cosine similarity classifier. That's called the ChaosNet architecture. Or we can feed it to a conventional machine learning algorithm, like support vector machines or even a deep neural network. So you have these two possible branches after that. You could either have a simple classifier or you could have a more sophisticated classifier. So this is this was the first thing that we published, what we call as ChaosNet, wherein the classifier is very, very simple. The classifier is just a simple, we extract the features of the chaotic trajectories and we store it as mean representation vectors. And when you get the test data, you do the same thing with the test data and then compare that with these representation vectors and see which is closest in a very simple dot product kind of a fashion, right? What is the closest to this vector? And then you declare the closest one to be that label. So it's a very simple classifier. So this is just showing you the same thing, right? So for example, you see this is actually a single neuron in operation. You have a single neuron which starts with an initial neural activity, say the value Q here, and it keeps firing. And the red one, what you see is the stimulus, the input data. And once it comes very close to the stimulus, we stop. And the green line that you see is called a discrimination threshold. Now, the Q and the B, right? They are the parameters which we need to learn. We need to train the network so that we can learn what is the optimal set of parameters for the discrimination threshold and for the neural activity, which will give us a good classification accuracy. So that is the one that we need to train them. Now, what is very, very important is that how are we guaranteed that this will work, right? How do we know that it works? This is where the properties of chaos comes into the picture. We know that these maps are ergodic. In fact, they're very, very well mixed maps. And topological transitivity guarantees that every trajectory, I mean, if you have a universal orbit, what's called a universal orbit is you have an orbit, you have an initial value, and you have a trajectory which will visit all neighborhoods. It will visit all neighborhoods. So we are guaranteed, chaos guarantees that such kind of orbits exist, such kind of trajectories exist. So which means what? Which means that it will come very close to the stimulus at some point in time, in some point in finite time. We're guaranteed by these properties. So that guarantees that the algorithm will stop. Otherwise, the problem is we can keep on firing, right? I mean, the neurons keep firing and they never come close to stimulus. That will not happen if we choose Q very wisely. That's the point I was trying to make, And then, as I said earlier, once the neuron stops, every neuron will stop at different time instance, right? Very much similar to the brain, you can say, that it's not necessary that the neurons have to stop at the same time. Some neurons can fire and stop very quickly. Some take a longer time to stop because they're hunting for the stimulus. Once they stop, we extract features from this neural trace, and we extract things like firing time, firing rate. Firing rate would be basically we're looking at what's the percentage of time which the neuronal trajectory is above the green line, the threshold, right? What's fraction of the time which is above the green line? That's called the firing rate. Then you can look at the energy of the whole thing. You can look at the entropy of the symbolic sequence. You can actually define a symbolic sequence based on, is it below the threshold, discrimination threshold, or above the discrimination threshold? You get a binary symbol, and you can compute the entropy. So the firing rate, for example, would be like what yesterday Professor Chakravarti talked about, right? This is like a rate code, right? This is like a rate coded neuron. The firing rate would be the rate of the neuron. So it's like a rate coded neuron. So it's very much like a neuroscience kind of an idea, right? So we use that feature. And as I said earlier, we have two possibilities, right? We can either feed these new features to a very simple classifier, or a more sophisticated classifier. You can choose, And we have tested in a whole bunch of data sets. And what is very impressive is that even with very low amount of data for training, like 0.05% of the training data, we get very good accuracies. We get accuracies as high as 98%. I'll show you in more detail what these numbers are. But this has been tested rigorously on a whole bunch of real world data sets. Okay, so I'm listing some of the data sets here. And I'll show you some results now. So this is probably what machine learning people will ask now. They show me the proof is in the pudding, right? Like show me the results, show me the numbers. So I'll show you in two parts. One is what we call the high training sample regime, which is we take the data sets. We're talking about classification. We're talking about classification tasks. So for example, if you go back here, for example, the IRIS data set, right? The first in the list here, IRIS data set. It's basically about classification of three kinds of plants, based on the length and width of the petal and sepal, and based on certain parameters. Or for example, look at you could have this breast cancer data set, or so basically we're trying to classify, is there cancer or no cancer, right? It's a classification problem based on certain parameters or certain features of the input data. So in the high training sample regime, we take the entire data and we split it to 80-20. I mean, this is the usual thing which machine learning people do. We train it. What I mean by training here is, remember the Q, the initial neural activity, the discrimination threshold B, and the epsilon, because epsilon is telling you the neighborhood, right? When do you stop? That determined by epsilon, right? So Q, B, and epsilon has to be tuned now, has to be trained. So we search for the best Q, epsilon, and B, so that we get a very good accuracy metrics for the training data set. And then once we freeze on that, then we apply it on the test data set. It's a very normal machine learning paradigm. So this is sort of a summary of for 9 data sets results you can see. And remember, we have two different classifiers. One is the simple cosine similarity based classifier, the chaos-net architecture. The other one is a more sophisticated classifier wherein we feed the features extracted from the neural trace to a machine learning algorithm. And here we have taken 6 different machine learning algorithms: decision tree, random forest, AdaBoost, support vector machines, nearest neighbor, k nearest neighbor classifier, and Gaussian neighbors classifier. We could choose more as well. And the question that we're asking is, does the chaotic features, the features extracted from the neural trace, can it boost the performance of these ML architectures? And notice the graph, the bar chart in the bottom of the slide here. You will notice the blue guys, right? The blue guys are the result, the macro F1 score. It's one of the performance metric. If you use the features fed to the ML algorithm, right? And the one which is not colored is the one which is a standalone algorithm. So for example, if you look at say AB and CFX plus AB, right? In the middle of the graph, AB will tell you that if you use AdaBoost, what kind of accuracy do you get on this particular classification task? It's a spoken digit classification task here. You get some whatever 0.1 or something, right? If you use the chaos features X, that's the blue one, you see that there's a boost, there's a improvement in the classification. And the green one, which you see on the leftmost part, that is the chaos net, which is the simple classifier, wherein we don't feed it to any other ML algorithm. We just use a very simple cosine similarity measure. So this is the kind of a thing. So this is actually trying to give you an overall picture of how it performs. So let me try and, we compute what is called the boost parameter. I mean, it's a performance metric. And the idea of a boost is how much are we boosting the performance of traditional ML algorithms by using these chaos-based features, right? Features extracted from the neural trace of these GLS neurons. And let's say, for example, you look at, say, the Haberman survival data set, for example, Haberman survival data set. If you use the ChaosNet architecture, which is a very simple classifier, you get 0.56, not that great. But if you use it if you feed the features to a AdaBoost algorithm, machine learning algorithm, you get a 20.59% boost, and you get all the way to 0.609 F1 score. And you notice that in many cases, the chaos-based features are actually doing a good job, right? They're enabling an improvement in the performance of traditional ML algorithms. That's the kind of idea, and more details are there in the paper. Now, the low training sample regime is where it gets very, very interesting. We ask the question, what if you train only on a few samples, like 1 sample per class, 2 samples per class, and so on and so forth, up to 9 samples per class. And we do this kind of an experiment where we train it with only up to 10 samples per class, but we test it on rest of the data, whatever the data is available, right? The test data, we test it on that. The learning has happened for only few. And here it's also very, very impressive that the chaos-based features are actually helping the conventional algorithms to boost the performance in the low training sample regime. So, for example, if you look at say the seats data set here, in the table, the last but one row, notice that for pretty much all the algorithms, decision tree, random forest, AdaBoost, KNN, for all these algorithms, the features are enabling the ML algorithm to boost its performance when we give the chaos-based features in the low training sample regime. That's what we have found. Yeah. So, and of course, just to give you one more example, we also looked at genome classification, right, for COVID-19 application. So we have the SARS-CoV-2 genome sequences, and we have other genome sequences from other, like SARS-CoV-1, MERS virus, and other viruses. Can we do this classification? And here also, what we found is that chaos-based features does an impressive job. That even with just 1 sample, we get a huge, very, very good accuracy of 0.9, greater than 0.99. And of course, we have done 1,000 independent random trials because we know that we're not overfitting, right, basically. And similarly, if you do a multi-class classification problem, you have 5-class classification problem. Again, the results are quite impressive. And remember, here we're using the chaos effects fed to an SVM, a support vector machine. So that does the best actually here. That's what we found. So we find this consistently, right? These chaos-based features are doing a very good job, in trying to boost the performance of existing ML algorithms. Okay, now where is noise in this whole picture, right? That's the question you might ask, because if you recall, the promise that I made is chaos plus noise is learning, right? What's the role of noise? This is where it gets very, very interesting. The role of Epsilon. What does Epsilon really do? Now, remember what I told you, right? You have the GLS neurons in the input layer. You have the input data coming in, and the neuron keeps firing until it finds the stimulus. What I mean by finds the stimulus is it comes to an epsilon neighborhood of the stimulus. Now, if you take epsilon equal to 0, you will never, I mean, from a probabilistic point of view, you will never hit the stimulus, right? That corresponds to 0 noise. Now, if you keep epsilon very large, then you probably hit the stimulus very quickly. And it's only the intermediate value of epsilon wherein you get something which is you get a trajectory which has certain interesting features. So here the epsilon, it can be seen as noise. Basically, what is epsilon telling you? Epsilon is telling you how inaccurately I want to approximate the stimulus. I really don't want to go and hit the stimulus with high accuracy. Epsilon is that region of uncertainty, right? That noisy measurement, basically. So, and I'll just show you this graphic here. Notice the rightmost graph here. The noise intensity is the x-axis and the accuracy is the y-axis. This is actually for a very simple 2-class classification problem. It's an intermediate amount of noise, the epsilon value, right? That intermediate amount of uncertainty in the measurement of the stimulus gives us very, very good accuracies. Whereas if you keep epsilon very small, that is low noise, or if you keep epsilon very high, that is, epsilon low would be low noise and epsilon high would be high noise. Both of these other extremes are not very good. It's only the intermediate amount of noise that actually does the job for us. And this is actually called, this whole thing about stochastic resonance, right? That you have this, for linear systems, we know that noise degrades performance of linear systems. Whereas in nonlinear systems, under certain conditions, and for certain nonlinear systems, noise could actually be good. Noise could enhance performance, right? And you see this kind of a behavior, right? That the optimal performance is achieved at an intermediate value of noise. This whole field is called stochastic resonance, and it's very, very popular in nonlinear systems studies, right? And it has a very nice backing in terms of evolutionary processes, right? That we know that stochastic resonance has been found in crayfish mechanosensory neurons, in the behavior of paddlefish, So it's actually a sensory adaptation. The evolution has found a way to use noise in the environment to boost its performance. And people have also used this idea in cochlear implants. So people who have hard of hearing, you have these cochlear implants which stimulates the auditory nerve. What they found is that if you add noise to the input data before they pass it to the auditory nerve, that intermediate amount of noise is actually good for recognizing the sound. So it actually helps. The noise actually helps. So, and it's also hypothesized that probably something like this is probably happening in the brain. Recall what I told you, that at a subthalamic neuron in the brain, we have noise levels which are very, very high. We have like minus 29 decibel SNR. It's huge amount of noise. So probably noise is playing a role, and we already know that there's chaos. So noise and chaos are probably playing a role in terms of learning, right? And this again, just to show you an example of spoken digit classification. So here you have this a speaker, speaking 0, 1, 2, 3, 9, and we want to recognize that. Again, we do the training and then testing, and we notice that, as you can see the graph here, this is just for chaos net architecture, but it's also true for chaos effects with SVM or other algorithms. You have this performance where for intermediate amount of noise, you get very good accuracies, very good performance metrics. Whereas if you have high noise and low noise, you really don't get good performance. So there's this argument that we're trying to make, that noise is actually good in our system. The neurochaos learning architecture, noise and chaos, they mix together to create this stochastic resonance. And probably something like this is happening in the brain. Of course, the brain, it's probably much more complex, and we really don't know what's happening, but maybe there is a reason why noise and chaos are they're playing together to create this kind of efficient processing in the brain. So this is sort of a bird's eye view of how do you compare neurochaos learning with ANNs or deep learning. So yeah, I think so one can look at it. The argument mainly is that we have a very different, we don't use backpropagation, we don't have activation functions, right? And our neurons are not dumb, right? They're intelligent, chaotic neurons which are tuned, right? Because we're tuning the value for Q and B, right? So we're tuning the map, actually. Basically, we're tuning the map in some sense. And it's an intelligent neuron which is learning the stimulus. So somewhat like the brain. Of course, we're still far away from the brain, but it's one step in the right direction is what we believe. And there's several properties of neurochaos learning. Shortage of time, I'll not go into the details, but we have actually shown mathematically that the neurochaos learning architecture can approximate very efficiently various functions. So it's a what's called the universal approximation theorem. And this is actually guaranteed by topological transitivity and dense universal orbits in these maps. So it's very much the property of chaos which is enabling such guarantees that we can give, that we can approximate any decision boundary that you might have. And of course, if you remember, I had made this point that it's like a rate-coded neuron. But interestingly, we could not use GLS neurons. We could actually use a spiking neuronal model as well. We have found that it also works. In the neural architecture, instead of using GLS neurons, we can use, for example, this Hinmarsh-Rose neural model, which is a three-dimensional differential equation in the chaotic regime. And this would also do the job for us. You chose GLS neurons because of those beautiful properties of lambda equal to h, the Lyapunov exponent is equal to the entropy. For those reasons, we use the GLS neurons, but we could also use a spiking neural model. So in that sense, NL is very, very flexible. You could use a rate-coded neuron, or you could use a spiking neuronal model, and you could combine with ML algorithms as well. So in all these cases, it works. Of course, it's all about tuning those parameters nicely so that you get good accuracies. And there are a whole bunch of other properties which I will not go into in the interest of time. For example, this notion of continual learning, and like as you get more and more tasks, what will happen to neural networks, right? They forget what they've learned. It's called catastrophic forgetting. Now, NL also has forgetting, but the rate of forgetting is lower in our architecture than in deep learning, and so on and so forth. And this whole thing about preservation of causality, that's something which Aditi will talk later. So NL has these amazing properties. Sort of to conclude, briefly to conclude, we know that there is chaos in the brain, the neurochaos, the notion of neurochaos at various spatiotemporal scales. And we want to use that kind of a principle in designing an architecture for learning, where there is chaos intrinsically in the neuronal level itself, and we show that we could also combine it with the traditional ML algorithms to boost their performance. We don't have any backpropagation. We just have very few hyperparameters. It's easy to interpret it, and this notion of how noise can help, because this notion of epsilon, right, that we are measuring the stimulus incorrectly or inaccurately. Noisy measurement of the stimulus is actually good. So the noise is actually playing a role here. So chaos plus noise is equal to learning. And recently we've also done some work wherein we've used logistic map neurons and GLS neurons, sort of a heterogeneous architecture, and we found that they do even better than what I showed you here. So that's actually in the work that is it's currently under review. So heterogeneous neurons are the way to go as well. We know that from biology as well. So neurocast learning is an interesting sangam of stochastic resonance, neuroscience ideas, machine learning, and chaos theory. But there's a lot more to be done. So given the context that we're talking about reservoir computing, so one way to understand it is that what's the connection between NL and reservoir computing? Of course, our group has been thinking about it. Myself, Hari Krishnan, and Aditi, we have been thinking about it. We don't have a concrete answer to this, but what we feel is the following: that each of the neurons in the NL architecture are like a reservoir with they're all parallel reservoirs, And unlike the reservoir computing, the input is, they're all having autonomous dynamics, right? Each of those GLS neurons are autonomous. I mean, they're just having their own dynamics. The input stops them, at some point. The input intervenes and stops it. Whereas in the reservoir computing, the input is driving it's sort of feeding into the reservoir, and the output is taken at some, you take snapshots of it, right? Here, the input is taking the snapshot, and it's asynchronous, right? Because the input value, each input value will stop every neuron at different times. So roughly, I mean, that's one way to look at it. And then we do feature extraction. That's probably like your the W out kind of a weights with the weight matrix that you have. So there's some mapping you can do for reservoir computing. But again, as I said, this is still very early to comment, and more work has to be done. And we would like to use other kinds of maps and flows to enrich the performance of neurocast learning. And I think the main question is, how is the brain able to function at such low SNRs? What we found in our method is that we can come down to like 5 decibels. We can't really go below that. But even up to 5 decibel SNR, we get something like 95% accuracy in many cases, So, but we can't go below 0. And deep learning is even worse than NL, in many cases. But of course, more rigorous work has to be done on this. So main thing is, I would say that neuroscience and nonlinear physics have to come together to really contribute to AI. And the applications are enormous, right? Neuromorphic computing, edge applications, few shot learning, the low training sample regime kind of thing, transfer learning and all that. And of course, the whole thing about causality and neurocast learning, that's another dimension which will be expounded by Aditi later. So I think I would like to end by saying that this is just the beginning. It's by no means an exhaustive, complete work. More work has to be done. And these are some of the publications that our group has produced on NL, and it's all available on my website. And there are other groups which have picked up some of our work and try to take it forward. There's one work by this group where they look at chaotic continual learning using our framework. And there's this deep chaos net. Like you notice that I had only one input layer, right? You could have multiple hidden layers, which we don't have in our framework right now, but we could use that. And all the code is available for free download and use. So I would sort of, would like for people to try it out and improve the algorithm further, because I don't think this is actually the beginning, and more work has to be done. So with that, I will end my talk, and people can write. If you have any questions, of course, you can ask me today in this forum. We have 10 more minutes, I think. But even otherwise, people are free to email me, and I hope that you had a good time listening to this talk, and I would like to hear your views and feedback on this ideas. Thank you very much. Yeah. I'm going to stop sharing now.
Yeah. So thank you, Nithin. Questions? There's one on the screen, please. Have a look.
Okay, I'll open the chat, I guess.
Yeah.
Oh, okay. So Vijendran, if you want, you can go ahead and articulate. I mean, if you want me to read it, I can read it. But if you want to ask me also, you can go ahead and ask me.
Yeah, I was having a curious question. See, for example, if you give an XOR problem in the form of an image, say a 128 by 128 image, okay. I was curious to know how the extracted feature look like. I mean, is it very close to 10 or what is the kind of, how does it?
Okay. Yeah, very interesting question. Actually, so this XOR problem is something that we are currently working on. And in fact, there's going to be a paper presentation by my student in the CNSD conference, but we have not looked at XOR from an image point of view. So what you're saying is more from an image point of view. We were looking at more from a logic point of view, just the table itself. How can we learn? And but we don't have an answer to the question that you have specifically asked, that you're asking about images as inputs, right?
That's correct. That's correct.
So,
No, it's
we don't know, but we would definitely like to try it out,
Yeah.
But we do have some understanding of how we can connect the neurons to solve the XOR problem and things of that. So we have some results there.
Okay.
And yeah, that is something, but not the images. It's just about data, Okay, in general, let me make a comment which will help the audience as well, that we found that our methods are very good for time series kind of data, text data, more like sequential data, sequential data like time series, speech data, text data. Images, it's not that great. It's not very bad. With traditional ML and our features, we do get close to the benchmark results, but we don't beat them. But we find that our methods are more, they're very good for sequential data typically, But I'm sure that with other kinds of neurons and other kinds of tweaking the architecture, we might do well for images as well.
If I may, one more question.
Sure, please go ahead. Yeah.
Your epsilon varies with respect to the extracted feature and eventual classification. I mean, what I mean to say is, if epsilon needs to be changed drastically, or it hovers only in certain range.
Oh, okay. Yeah, very good question again. So typically, what happens is that if you look at some of the graphs I showed, right, there is no one range of epsilon where we get very good results, So of course, low epsilon and high epsilon are more or less ruled out. I mean, they never happen. It's only the intermediate region, but there are multiple local maximas, So there are multiple values of epsilon range where we get good performance. Sometimes it's true that they may all be very close to each other, but sometimes they may be very sensitive. So it's not that straightforward, in that sense. You might have noticed that it's not like I have a single hump, It's not a very nice global stochastic resonance. We call it as local SR. We call it as local stochastic resonance. So there are regions of epsilon where we do very well,
Okay. Thank you.
Thank you. Thank you for the question. Yeah.
Any more questions?
Professor, if I could ask.
Oh, please go ahead. Please go ahead. Yeah.
Yeah. With respect to the causality, wouldn't it be dependent on the amount of information that is available to the network?
Okay, so you're asking the question
Wouldn't it
about
be a relative factor? The causality, there was this differentiation that you had put it in terms of between the deep network and the brain, where you had mentioned that in terms of deep networks, you generally tend to have correlation, whereas in terms of brain, you tend to have retrocausality. So even in terms of retrocausality, doesn't it actually make it specific to the amount of information and the exposure that the brain has actually had to that specific scenario?
I understood the question. So partly this is inspired by Julia Pearl, you might be familiar with. So the argument is the following. It's not to do with the data per se. It's got to do with the way you are looking at the data. So for example, the argument is that we human beings, right, we intervene, we do an intervention in the world. We do an intervention and then we collect data. That gives us a higher level of causality. Whereas deep neural network is more like a post-mortem, right? You already have the data. You're not doing an intervention into the world outside there. You collect the data and then you look at correlations to infer about causality, which is valid to some extent. But if you want to do true causality estimation, then you need to do this intervention and more importantly, counterfactual reasoning. So of course, there are all these current trends where people are trying to merge the two. And Aditi later will talk about some of these ideas, So it's not really the amount of data per se. It's about the causal model. Deep learning does not have a causal model of the world, right? It has nothing. Whereas we human beings or even animals, right? We have a causal model of the world. We roughly know how the world works. We have an intuitive physics, intuitive biology, intuitive psychology. So we have a model of the world and we collect the data. Whereas deep learning doesn't have a causal model of the data in itself, That's the big difference. There's no model to the data. It's not about the amount of data. It's about the model, So that's one way to look at it. But these are valid questions. And yeah, I mean, we have to explore more. Yeah.
One other question, Professor.
Sure, go ahead,
has something in terms of testing the fractal curves been tried out in the chaos net model?
So are you asking to learn, in order to learn fractals? Is that what you're asking?
Learn and classify fractals, feature
No, we
classification.
haven't done that. Actually, in fact, one thing that we are trying to do is, can we use fractals for learning? I mean, rather than learning fractals, that is something that we are looking at. But what you're saying is also interesting, which we have not done that. We could also do that. Like we give fractals and non-fractals, and can we learn that? I mean, it's a good idea, and we should try it out. We haven't done that. But we were thinking more in terms of how to use other properties of chaos. We have used topological transitivity, we have used ergodicity, we have used non-periodic. I mean, we have used all these ideas in our work to do the classification. But fractals is something which we are not directly used. So can fractals help us? For example, if you look at the whole data compression algorithms, right? So this whole Doboshi's wavelets, it's one of the best wavelets actually. It turns out that that wavelet is actually a fractal. It turned out that that wavelet has a fractal structure to it, and maybe that's why it's optimal for data compression. So it turns out that fractal seems to emerge everywhere, right? So whenever you have a dynamical system, there's always a fractal lurking, right? So the question to ask is, in learning tasks, are the fractals emerging out somewhere? We don't know the answer to that. And that is one side of the story. And what you're saying is also interesting. Can we learn fractals, and how would that look for ChaosNet? We haven't done that experiment so far. But thank you for your questions and suggestions.
Sure.
Yeah.
Thank you.
There's a question in your chat from Sarthak.
Yeah, Sarthak, do you want to go ahead and ask the question? That's easier if you want to do that.
Yeah, I just want. One second.
Go ahead.
Yeah.
Go ahead, Sarthak. Yeah.
So maybe I missed this. So are these parameters? I mean, do you always have like a homogeneous system where like your epsilon, q, b parameters are like just the same for every node, or have you tried like putting heterogeneity into those?
Yeah. So
and also,
right
how
now,
exactly do you end up?
For the sake of computational complexity, we have the same for all the neurons right now. But recall that I also made a point that we use logistic map and GLS maps together. We use it. I mean, we have a very simple architecture, which I didn't talk in the talk. We have, for odd locations, we have GLS neurons, and even locations, we have logistic neurons. The logistic neurons will have R value, right? The bifurcation parameter, which we tune. And for GLS, we tune the B value. But for the whole class, we have the same setting. But you could also do what you're saying. That will be more computationally intensive. That's all. You allow for that degree of freedom. You could do that and tune everything independently, which is probably what I don't know whether the brain is doing that, because they talk about this thing about that there's a single neuron which will identify an image, for example, in the brain and things like that. That there's a specific neuron when you see the picture of somebody, right? And so maybe we can even tune at that level. It's possible, but we don't do it for computational reasons.
Yeah. I guess my other quick question is just broadly, how do you choose these parameters? Like, is this just
so
right
broad
now, hyperparameter tuning kind of?
Yeah. So right now we do sort of a very dumb brute force grid search. That's what we're doing right now. So what we do is we do a grid search for QB epsilon, and we do cross validation to find out. So it's just a loop. Like we do the cross validation on the training data, and then we find out grid search, and then we do it and then we freeze it and test it on this data. But we haven't been able to figure out a more principled way of optimization. We haven't figured it out. So that's why I'm saying this is lot of scope for research actually here. Is there a principled way, like backpropagation, right? Like backpropagation, is there a way to propagate the errors backwards in this system? I mean, because ours is more complex, right? We have this chaotic system, so tuning them using some algorithm will be interesting, but it's not obvious how to do it. It's definitely a scope for future work. Yeah, we do just brute force grid search. That's all. Yeah. Thank you for your questions. Yeah.
Anybody else?
Hello, Nithin.
Yeah, go ahead, Swamindeep. Yeah.
Yeah, I just had a general question. So, are there any statistical underpinnings to justify many of the observations you have made? Means it's a just broad brush question. So,
can you be more specific when you say statistical?
Specific means, suppose in a framework of statistical learning theory, you have like in a neural net, like a VC dimension and all those stuff. So, are there any parallel things to do here for in this case?
Yeah, no, it's a good question, and we have been thinking about this VC dimension ourselves, in our group, but we don't really
like the capacity of neural nets kind of thing, right?
Capacity,
the statistical learning framework.
Okay, see, one thing I can tell you, maybe this is not really a direct answer to your question, but we try to look at the Liouville experiment. See, what we thought was there was this hypothesis by Sprott. The Sprott has written a nice paper saying, "Is chaos good for learning?" And he argues that weak chaos is good for learning and not strong chaos. We did not find that in our architecture. For example, Liouville experiments were all over the place. It was not that. In fact, in some cases, very rare cases, even negative Liouville experiments was fine. That means no chaos. But typically, they're all positive Liouville experiments, because remember, the theory of learning now has to be more dynamical, right? I mean, we need a dynamical systems theory now, right?
Yes.
But bridging into VC dimension and all is also important. we haven't been able to do anything in that direction yet, you know. It's a good question you're asking. I mean, we don't know.
Yeah, there is a lot of avenues for further work in this area. What I
agreed. I think so because we want to go more closer to the brain, you know. I mean, I know we're still far away, but it's at least one step in that direction, I feel, you know.
Okay,
thank you.
I think Nithin, did you display your email anywhere?
Maybe,
yeah. Maybe you could just show it to people for a minute so that
yes, I will.
That people could write to you.
Definitely, yeah. So this is my email ID, nithin@nias.res.in. Please feel free to drop in an email, and all the code is available on GitHub, so people can just download and use it. Everything is available on, and you could reproduce all the results in the papers as well.
Okay, so thank you so much, Nithin. It was great hearing you again, and I hope we'll see you in person soon. You are next door after all. And
thank you very much. Yeah, I do look forward to meeting you in person.
Do come whenever, as soon as you can.